So just a brief introduction of myself. I was with Washington State University before, where I got this Western States grant to host this event. And this is why I'm still here, hosting event for Western States. But now I moved to University of Connecticut last year. So when I was hired to Washington State University 7 years ago, I was really, really excited, and I was also very, very scared because all my career before then, I was working on the cropping systems in the eastern part of the US and Midwest. And the cropping systems that I was working on was very simple: corn after corn after corn, or corn after soybean, corn after soybean, corn after soybean. So when I went to Washington State, Eastern Washington State cropping systems, I'm like, oh my God. So now I understand truly what variability means, right? So they have so many different types of cropping systems and soils and weather conditions and micro weather. It's just so many variabilities. And I was hired as a soil fertility specialist. I was supposed to give recommendations for the farmers on their fertility management. So I look back the history of their nutrient management systems. While this very similar to Midwest, everyone uses one single number for all crops, different types of crops, and for all the environments. Basically, for the whole state, you use one number. So and after talking to the farmers, look at their fields. I mean, like so many variability, and how could I feel comfortable giving them one number? And also, I was supposed to run new trials and generate a new number. What is the point that I spend so much money when that number doesn't even work anywhere, right? So today, I'm just gonna present some spatial variability, temporal variability that I encountered in the Washington State, and which drive me to this group of on-farm precision ag as I was looking for more efficient way of running trials that will generate data that are actually meaningful and usable. So, and I will just show a few examples of cross-field temporal variabilities and within field spatial temporal variabilities, and some factors that contribute to those variabilities. So here, the first spatial variability across field and across time that I encountered was unit nitrogen requirement. So basically, unit nitrogen requirement means a pounds of nitrogen that's required to produce, say, a bushel acre of yield, right? And we're looking at 8 varieties here and grown into different years, into different locations. You can see that within 1 year, the unit nitrogen requirement could vary from 4.76 to 6.4. Huge variability, right? And you use the same variety and you look at different years, again, you have different unit nitrogen requirement, right? So which one do I give it to farmer? Do I just average it out and give the average number to the farmer, right? And now we're looking at another example of differences in unit nitrogen requirement that varies depending on the yield potential, right? If you happen to have a field that's very productive, your unit nitrogen requirement is only 6, right? But if you are working on a field that has much smaller yield potential, then that unit nitrogen requirement could be double, even triple. So which number do I give to the farmer? Do I give an average number again? So what does this mean? So how do I use this information? How comfortable I am saying, hey, if you are in if you have that yield potential, you use this. I don't know if that's the right thing to do. So how do I comfortably derive data, and then I can comfortably, with high confidence, and tell farmer, hey, this is what you do, right? So, and the next variability that I encountered was weather. Wow. every mile you drive, you would have a completely different climate condition. And within a field, you have huge microclimate within a hill. I'm going to show you what I mean within that little hill. So here we're looking at how canola seed oil responds to nitrogen application timing in different agroecological zones of Eastern Washington state, right? So agroecological zones were categorized based on cropping systems and climate and so on. So we are going to just look at comparison between fall application, split application, and spring application, right? So according to those 7 sites that we conducted in 2 years, so if you were in green fallow or transition zones, either you apply nitrogen in spring or split apply, right? So you would end up with similar seed oil content. But if you are in high rainfall zone or irrigated zone, then applying your nitrogen in spring would result in much lower oil concentration. What does this mean? What does this mean, right? That means that you would have a lot higher protein concentration in the oil seed. So now there's no premium that based on oil concentration now, but eventually if there is, then when you apply fertilizers will make big difference in terms of your economic return, right? And again, what does that mean? How do I make recommendations to the farmers? Because there are, again, so many different variabilities that is getting into this, right? So how do I give them site-specific recommendations? So another variability that I encountered was other management practices like tillage, right? And like conventional till versus say reduced tillage versus no-till. Tillage can have big impact on your soil property, chemical, biological, and physical properties. And those change of those soil properties can have big impact on your nutrient cycling, for example, your nitrogen cycling, right? So if you have practiced consistent no-till, you would have much better soil structure, which means you have a lot better water infiltration. That means if you are in high rainfall zone, and then you apply your nitrogen in the wrong time, you can lose a lot. But if you are in lower rainfall zone, you wouldn't have that issue. So there are just so many things that we need to consider when we give recommendations to the farmers. Here we're looking at how tillage impacts soil pH, right? So if you practice conventional tillage, then you would have less problems run into low pH problems. But people started seeing low pH problems, but still smaller than if you had no-till, right? If you have no-till fields, you would have high probability that you run into very, very low soil pH and stratified low soil pH. So what does this mean? How does it impact my nitrogen management? Of course it does. Why? In many different ways, right? Why do we acidify our soils? Because we apply too much, we're applying fertilizers, right? Especially nitrogen fertilizers, phosphorus fertilizers, sulfur fertilizers. Those are the management that cause the soil acidification problems. So that's one thing. So we need to manage our nitrogen better so that we at least slow down the impact to our soil. On the other hand, if you have too low pH, your nitrogen cycling is impacted. So that means your nitrogen is not like the conversion or transformation of nitrogen fertilizers you apply to the forms that your crops can take up is impacted. So that means you're losing more, or your fertilizers are sitting there, not be able to take up by your crop, right? So, and here we're looking at a survey conducted in Columbia County in Washington State, comparing pH after so many years of farming, comparing with the sites where you never farmed, right? You can see that the pH get a lot lower after so many years of farming. And here I have so those are the data that we collected from a research that we conducted in the Midwest. We surveyed over 3,000 cornfields and looking at the major factors that impact the corn nitrogen sufficiency level. So basically, I'm just going to use the nitrogen time, application time and form as an example, like how we interpret this thing. So say you use hydrous ammonia as source of nitrogen fertilizers, right? So, and comparing fall applications, sedge-rest applications to spring applications, which one is more efficient, right? So we're looking at odds of corn nitrogen sufficiency level at a higher nitrogen sufficiency level, right? So if we are comparing within the form of AA, we can see that in all those 3,000 fields and holding all other variables the same, if you spring application of hydrous ammonia is a lot more efficient than if you apply it in fall, right? And then use tillage as an example, right? So compared with conventionally tilled fields, no-till fields, you would have a lot less odds to have your corn nitrogen sufficient level at higher level. But anyway, so those are all significant factors that impact your nitrogen sufficiency or nitrogen cycling or nitrogen uptake or nitrogen loss. So all those have big impact. And then I move into then field spatial variability. So first foremost, of course, we look at spatial variability of yield and protein, right? And you can see, so here, just as example, this field, the lowest yield was less than 40 bushel per acre, but highest yield was more than 150 bushel per acre in that single field. And protein varied from less than 7% to more than 12%, right? And moving to another spatial variability, right? So here we're looking at 17 years cumulative residue production in this field, right? So the total residue production could vary from 42 megagram per hectare to more than 113, right? So again, so what does that mean to our fertility management? Of course, it has big impact, especially if you are, say, you practice no-till, right? What form of fertilizer you use, where you apply, right? You apply it on the soil surface, and where you have huge amount of crop residue, you would have low nitrogen use efficiency because that crop residue will fix your nitrogen that you applied on the soil surface. And the more residue you have on the surface, the more nitrogen get fixed, not available for the current crop season, right? And then the spatial variability of crop residue production will result in spatial variability of your carbon stock, right? And what does that mean to nitrogen management or any other fertilizer management? Big impact. Why? Because your organic matter is where your nitrogen or a lot of other fertilizer is from, nitrogen, especially nitrogen and sulfur, right? So say you have, just give you a book value for every 1% of organic matter, and you have mineralization rate of 20 pounds per acre, right? And then another location field, you have 3% of organic matter, which means you have 60 pounds per acre of nitrogen from soil, right? And sometimes you have really high, some years you have really high nitrogen mineralization rate, could be as high as 50 pounds per acre for every 1% of organic matter. So then you would have huge spatial variability in terms of your nitrogen supply from your soil, right? So that's a factor that we cannot simply ignore and tell everybody just use this number, right? So now we're looking at some piece of information that we can use using our sensors, like protein sensors and yield sensor. So when we have those two data together, we can easily calculate how much nitrogen we're removing from harvest of grain and map it out. And even better, because the nitrogen removal index is pretty consistent for wheat, right? And using the nitrogen harvest index and how much nitrogen is in the grain, we can easily calculate total nitrogen uptake. Now we have a map of total nitrogen uptake. We have much better information than just yield map itself to make decision upon for future nitrogen management. So, and this is another variability that we encountered. So, okay, so many of our speakers were using satellite imagery, drone imagery, right? So what is the best time that we should go out and take the imagery that correlate to our yield or quality the best, right? And different time of the year at different crop growth stage, you have different strength of correlation to the imagery, right? And happens to be that year for winter wheat, the end of June to early July was the best time to go out. And that corresponds to the crop growth stage of from flag leaves to the early grain filling stage. And here's another study that was looking at the correlation between NDRE or DVI to the crop nitrogen uptake. They also, so this study was conducted in Idaho, where our study was conducted in Washington State. And both studies found very good correlation between those indices and the crop nitrogen uptake. And the relationship was pretty consistent from year to year and from crop class of wheat to class of wheat. And they were looking at predicted nitrogen uptake with the true ground truth, and they found very good prediction using those models. So, and now, so what are the factors contributing to those? So this is like why I said I was scared, right? So when I was a student, I was told that you do not farm on the slopes that's higher than 15 degrees, because then you would have significant erosion problems. We do not recommend people to farm on steep hills, but look at this, right? Very typical field, and farmers farm on the slopes that are higher than 30 degrees, right? And that means there's huge spatial variability in terms of your soil, right? Soil fertilities, organic matter, soil depth, hydrological properties, your microclimate, all those have big impact on your crop productivity, right? And of course, it has impact on how we make our decisions on our fertility management. So yell at me if I'm going over time. So here we're looking at a digital elevation model of a field in Idaho. And this field has a really, really steep slope. So basically when I'm in the bottom, nice, and just comfortable. And then when I get on the top of the hill, windy, cold, and poor soil, very sandy soil, a lot of erosion, right? So based on digital elevation model, we can derive out many indices, and those indices represent or can approximate the climate or like temperature, like solar energy, and those things. And all those things could have significant correlation with the crop productivity, right? And I'm going to use all of those indices to show you the variability caused by those indices, right? So here we're looking at in that field in that year. So you'll have average a lot higher yield in concave locations comparing with convex locations. But that means it's just that year in that field. in another year, if you have a wetter year, then it could be completely opposite, right? Because again, say if you have this convex location, then in a wetter year, that's where you are collecting water, right? And you would have a lot of nitrogen leaching loss and nitrogen denitrification loss, right? You would have severe nitrogen deficiency problems. But anyway, so you would see the trends, how the curvatures impact your yield and protein and total nitrogen uptake. So here we're also looking at how yield differences in different classes of slopes. And you can also see that the yield varies based on the slopes and also based on aspect, right? So like say this particular year in this particular field and south-facing slope, you had higher yield than the north-facing slope. You got higher yield than south-facing slope. But in another year, say if you have a hotter year, then you could have completely opposite, right? So this is why we need to conduct trials more than just 1 year. We need to conduct trials on the same field for a number of years, and how many I'm not sure yet. But eventually we will hopefully figure it out, right? We can. And then, so based on so many years of data, we will be able to predict, hey, in this kind of weather condition, you would have this type of yield in this location. And hopefully we can reach that goal. So, and here's another example of what is causing spatial variability. Almost there, okay. So I'm gonna pass this. So, and then, so in Washington State, the soil depth is very, very important for yield, right? So because we depend on the stored water to produce yield because of our Mediterranean climate conditions, right? So we have huge spatial variabilities in terms of soil depth, right? When you have spatial variability in soil depth, you would have spatial variability of your rooting depth, which means you have spatial variability for your roots, you know, to capacity of your roots to explore for nutrients and water. So, which means the shallower your roots restrictive layer is, the more water get left behind, more nitrogen get left behind, and less nitrogen use efficiency. So how do we include those information in our decision making? And then, and of course, other spatial variability, pH, organic matter, and those kind of things. And another thing is why pH is so important, because it impacts the nutrients availability, right? So, and so after presenting all those variabilities, there's only one thing I want to say. In addition to crop yield quality, isoplant maps as planet maps, so it's important to collect other information that have big impact on your input efficiency. Thank you.